Right, thank you very much for the introduction. As Igor just said, I'll be talking about electron impact ionization of tungsten ions, and I will try to, within this short time, to report on the progress we have achieved at our institute and with our collaborators. So what do we need it for? There has been also already some information said. For big tokamaks, there is a plan to install diverter elements, diverter electrodes, which are made of tungsten, mainly for the reason because this is extremely sustainable material. But nevertheless, it's possible that under extreme conditions it gets melted, evaporated, and tungsten inevitably gets into the plasma and may prevent it from reaching the needed temperature. So for this reason, a huge amount of atomic data of what is very important of high accuracy is required in order to be able to model these probable losses in the plasma temperature. So this is the experimental setup we use in Gießen in order to measure electron impact ionization cross-sections of tungsten ions. We produce tungsten ions by inserting tungsten hexacarbonyl into the plasma of our ECR ion source. And then tungsten ions, together with other ions, get extracted. They are let into the first analyzing magnet, and by changing the field of a magnet, we can measure such beautiful single isotope resolved mass spectra. And by setting the right magnetic field, we can choose the ion we would like to study. And we let it into the interaction chamber where the ion beam meets a ribbon-shaped high-power electron beam, which maximum electron energy could reach 1,000 electron volts at 450 milliamperes of total electron current. Further, primary ion beam and product ion beam, they are separated by the second analyzing magnet, and its field is set so that the product beam goes into the detector chamber and the primary beam gets catched by one of the two movable Faraday cups. So here are the results. Here we show the measured cross-sections for these charge states. Here they are shown in the form of fine-step energy scans normalized on the separately measured absolute data points. So the scale is absolute here. And just shortly to describe it, until the charges of 8 plus, we can see a certain structure on the measured cross-sections which tell us about the different ionization mechanisms which occur. And the rest of the cross-section have very smooth shape, but it doesn't mean that we have to deal with it just with a direct process. So there are still a lot of different ionization mechanisms which occur. Shortly considering the literature, these charge states have been measured previously by Stenke et al. And yeah, I also have to show you the comparison. It looks good, especially for tungsten 5+. And for tungsten 8+, for example, we can see some sort of discrepancy, but it's still within the error bars, and it mostly comes from the metastable, different amounts of metastable components which have been present in both experiments. And metastable components, this is quite a complication when we deal with such kind of experiments. There has been also a theory performed by Penzola and Griffin in 1997. Here it is showed with a red curve. And it has really remarkable agreement, but however, they did not include the compound of the metastable states, and which, I don't know why, they should have knew about that. And of course, I have to mention the extensive work of Loch et al., which they have performed rather recently on the whole isonuclear sequence of tungsten ions. As I said, the calculations of Pinzola et al., they haven't included the metastable component. And since previously we had success on describing ionization cross-sections of xenon and tin ions by ourselves, we have tried it also for tungsten 5+. And as you can see, it wasn't really successful. So at least we haven't been happy, even by including some amount of metastable states in our calculations. So we asked our colleagues from Vilnius in order to produce calculations for us, and they did it for us with a level-to-level approximation. And this is the result which they have reached. So in this energy region, the agreement is very good, but there is still some space for improvement here above, and the work is still going on. Also, there have been, I'm showing you the comparisons with the theoretical data because there's nothing else to compare. So now we come to tungsten 17+. Here I show our actually already published data from 2011 compared to the recent calculations of Zhang and Quan, also in level-to-level approach. For ground state and for first and lowest state of the first excited configuration, we can also observe quite good agreement, especially at higher energies. They're still a little bit lower, the calculations, but still within the error bars. There's one issue which they have noticed, and I think it is quite important. What they have found is that the calculated direct ionization cross-sections, calculated using the configuration average distorted wave method, which the one they have used was implemented in the London atomic physics code, and the cross-sections calculated using the FAC atomic code, also, but within a level-to-level approach, also distorted wave, they differ about 20%. And this is their clue on that. Why does it happen? However, we have privately communicated with Vilnius guys recently, just during this conference, and they said they have checked it, and it doesn't seem to be the case. So there is still quite an uncertainty. And finally, I'll show you the highest charge state we have measured. This is also compared with our calculations, and surprisingly here we got a very good agreement. And so here we had to include excitation out ionization processes along with the direct ionization. And we have done this for the ground state and as well for the excited state. So, but considering also the previous issue, the fact that we actually reached this perfect agreement, at least at these higher energies, doesn't mean we can really understand the problem. And in any way, it means that the approach that we use describes the system also well. Yeah, and there is also another issue in Loch et al. In their paper. They have assumed that the excitation optimization processes should not contribute much to such high charge state, and as we can see it from here, it seems not to be the case, not really be the case, but who knows. Yeah, finally, our goal was to generate plasma rate coefficients for plasma applications, especially for modeling of the influences on the Icpeac plasma. And we have performed this, as you can see it here. And as you probably noticed, we have performed this in a quite short temperature range. And the reason for that is while you're integrating, you have to take a special care on choosing the highest integration limit. Otherwise, this integral may not converge. I should probably also make a citation on where we have taken this from. So finally, let me come to the summary. There are three important points I would like you to take home. First one is that with tungsten ions, we have to deal with a huge amount of competing ionization mechanisms, which are really hard to take into account in the right way. Secondly, in the experiment, we have to deal with the admixtures of long-lived excited states in our ion beam, and they take part in the experiment, and this in no way makes our life easier. And here, for instance, in order to extend the temperature range for the plasma rate coefficients, well, normally we use, as we did it for xenon antennas, for example, we have used the theoretical data in order to extrapolate the experimental data energy range, which is quite limited. And in this way, we could extend the energy, well, the temperature range up to 1.6 keV or something like that. So in this case, we can only reach 80. Unfortunately. And if we would do this, for example, in the case of tungsten 19 plus, without knowing what is actually, for example, the real contribution of the direct ionization processes, this would be just a simple speculation. So for that, we would need to go experimentally at least 1 keV beyond the 1 keV present experimental energy limit. In order to get more information and in order to let theory orient better on our experiment. And such work is going on right now in our institute. This is our new electron gun, which is currently already working in our lab. This allows us to extend the energy range up to 3.5 keV, and it hopefully allows us to increase also the electron current, which would also allow us to measure, to get, let's say, deeper into the ions and let us reveal the processes with very small cross sections. And also, further level-to-level calculations, which have been figured out to be really important, this level-to-level method, are also very welcome. And here are the people, no, not yet. Here are the people who anyhow supported to this project, and I appreciate this support very much. And of course, thank you for your attention.